Sound intensity. Intensity is essentially related to the loudness of a sound. That's another way of describing intensity. But really what intensity is if you think about it, a vibrating object is pushing on the air all around it in all directions. So it makes like a spherical shaped compression all around the outside of it when it moves in all directions. And then that pushes out in a sort of a ever larger sphere, right? That goes out in all the directions from a vibrating object. So what that means is that the vibration has a certain amount of power associated with it. How quickly it's changing the energy of the air. And that power will be distributed over a small area at first, a small sort of sphere around the object. But as it spreads out, it goes out in all directions, it's covering a much larger and larger area. So the further away from a vibrating object you get, the less intense the sound becomes. It gets spread out. So we're going to look at that sort of ratio. So sound intensity, the loudness of a sound. So we use the word I for intensity, the letter I mean. And what we're really describing is I is the power involved in a vibration. So remember what power is. It's the work or energy change over a certain amount of time. And so a vibration, right, if it's a very, very slow vibration, it's changing the energy of the surrounding medium very slowly. And that would not be extreme power. It wouldn't be very much power. But if it's a very vigorous vibration, it would be changing that energy much more quickly. And that would mean more power. And so the more power there is, the louder the sound would become. So it's power, but it's also spread out over the area around the vibrating object. And so the unit would be the power unit, which is watts, and then per square meter for area. So that's the unit we use to describe intensity, watts per square meter. So let's just draw a picture to kind of illustrate what we mean. Let's say we have some vibrating object right here, and it's going to shake back and forth. Well, when it does, it will push the air in all directions. So it will make sort of a spherical shaped compression that will go in all directions. On the board, it just looks like a circle, but you have to think of it as a sphere, like a little basketball shape, because it's also coming out towards me and going in. It's going out in all the directions, right? And so if you imagine one of those, just one of the compressions moving, it would go so far, right? It would go this far, and its distance would be the radius of this little circle. That's how far it's gone, how far away it is. And if you think about that, and you draw another little line, say here, you can see if I go to red here, there's only a relatively small area of the sphere. Think of this as a piece of the skin of the basketball that the power would be spread out on, right? But as it spreads further, right, if we go out like this, further away, we'd have a circle like this. And then you can see that that would be spreading out over a much larger space, right? A larger area. So if you have the same amount of power, but it's spread out over a larger area, that means that you're going to have less overall intensity because it's being spread out. And it turns out that if we wanted to describe it mathematically, the area that it's being spread out is the surface area of a sphere. So the intensity would be the amount of power divided by the surface area of a sphere, which is 4 pi r squared. So that describes the intensity as it comes out from uh, from the center outwards. And of course, the further it goes, the bigger the bottom of this gets. And when the bottom of a fraction gets bigger, the whole fraction gets smaller, right? A half, a quarter, an eighth. The bottom, as the bottom becomes larger, the fraction itself is smaller. Okay. Now, more commonly than figuring out the actual watts per square meter, what we tend to do is we tend to do a little sort of a comparison ratio. I'm going to show you how that would be done. Okay. Let's start with the intensity at position 1, which I'm going to call position 1, right there, right? And we're going to also call this one position 2. But we want to compare those two intensities to see how much louder or softer they got. We could say that this would be power over 4 pi r 1 squared, right? Using the first radius. And then the intensity at the other position would be the same power, because it's the same vibration, but it's spread out over a bigger circle, which would have a bigger radius, r2. So we get this, right? Now, if we want to compare, if we want to compare and say, well, how much louder is I1 than I2? How is it 5 times louder? Is it 10 times louder? If we want to do a comparison, the way we do comparisons in math is by divisions. So we'll take a comparison of I1 and I2. We'll say, what would happen if I compare I1 compared to I2? Well, I1 is the same as P over 4 pi R1 squared divided by P over 4 pi R2 squared. That's what our I2 is equal to, right? So I'm replacing the i's with these things, which are exactly the same as them. And then we have to do some math. We have to divide by a fraction. Do you remember how to do that? Multiply by the reciprocal, right? So let's take the top of this fraction. So I1 compared to I2 is equal to P, the top of the fraction, 4 pi R1 squared, multiplied by the reciprocal. So flip that bottom part upside down, and it would be 4 pi R2 squared over P. See that? Then, okay, we look at this fraction and we see that some of these things are going to cancel out. So we get here, and you'll notice that there's a P on the top and the bottom. So if I divide the top and bottom by P, those disappear. I can also divide the top and bottom by 4 pi, which would eliminate those two things. Because remember, a fraction is like an equation. You can do the same thing to top and bottom without changing it, right? And that leaves me with, on the top, just this, R2 squared. And on the bottom, it leaves me with just this, R1 squared. And it gives us this nice little comparison ratio. Two things to notice. On the left side, it's I1 on top of I2. On the right side, it's R2 on top of R1 because of that reciprocal thing. So you got to not confuse that. And of course, the R's have to be squared. And so we can use that to figure out how much louder something is depending on how far away it is. I'll give you an example. Let's say we have a helicopter here. There's our helicopter. Little propeller there. Little helicopter here. Okay? And the helicopter is making a lot of noise. And so down here on the ground, we have a person right here. And we have a person way over here. And so the closest person is going to be this far away. let's say this person is 10 meters away. The other person is 30 meters away. Those are the R, right? You can imagine that the helicopter is at the center of the sphere of sound, and as it makes sound coming out in all directions, that sound is first going to hit the guy who's 10 meters away, but by the time it goes 30 meters, it will have spread out to a bigger circle, right? A bigger sphere. So what we'll do is we'll say, we'll call, this will be I1. I meant to do that in black. Still not going to let me do it in black. There we go. And this will be I2. So if we compare them, I1 compared to I2 equals R2 squared over R1 squared. And that equals R2, right, would be the 30 meters, because this is guy number 2. So that's 30 squared, and R1 would be 10 squared. So that comes down to, trouble with my board here, I1, try to go a little thinner, it's easier to see, compared to I2 equals, and that was 30 squared over 10 squared. So that's 900 over 100, which is basically just 9, right? So that means that I1 compared to I2 equals 9. If we multiply the I2 to the other side, we can see that it becomes a comparison. 9 I2. So in English, this says that the intensity at position 1, which is this side of the equation, is, right, or is equal to 9 times, well, the intensity at position 2. So it's 9 times louder for that guy who's closer than it is for the guy who's farther away. It doesn't give us an actual watts per square meter measurement, because when you're comparing, when you compare an I1 and an I2 in a fraction, the units cancel out. So there's no unit for this. It's just basically saying it's 9 times louder, right? That's all it basically means. So that's one way of looking at intensities. And we can do all kinds of interesting things with that. All right. That's all I needed to do in this video. So we will stop there, and